Welcome to Study Loop.
Let's evaluate this integral by considering several cases for k. So here are three cases that will cover every single case out there. Case 1, k0, case 2, positive k, and case 3, negative k. So in case 1, we can rewrite this integral as just 1 over x squared, and then use the power rule to evaluate that integral. So that would be the answer for k equals 0. Now let's consider the case when k is positive. So then we have 1 over x squared plus k. We can rewrite that as x squared plus radical k squared. And then we can use a trig sub here. Here we should take x to be radical k tan theta. Then dx radical k secant squared d theta. And then this integral can be written as radical k secant squared. It's a k over here. And then on bottom, when we square x, we get k times tangent squared. And then plus this k here. So let me go ahead and factor out that k. And then we use the fact that tan squared plus 1 is equal to secant squared. Pull out the constant. And then now, let's go to the next page since I'm running out of room here. We have root k over k times the integral of d theta, which is just theta. And then using our trig sub over here, x equals root k tangent, we could solve that for theta. So divide both sides by the radical, and then take the arctan on both sides. So that will be our value for theta. And then our constant of integration c. So this would be our answer in the case when k is a positive number. And then now let's finally go to case 3. This is when k is negative. So here we can rewrite this integral as, so basically here we have a negative number. So the way to look at this is a simple example. Like if we had x squared plus minus 4. So if k was a negative 4, you can write this in this form, and then you could do a difference of squares formula. So we can do this because k is negative. So in this case, it'll be x plus root negative k. And then x, so let me go back, I got a little sloppy there. We have a negative k in that radical, and the negative, we put the negative inside the radical because then if k is negative, that means negative k is positive. Dx, so this is what the author would call case 1. For the integrand, we have distinct linear factors. So just looking at the integrand, we can break that up as a over x plus the first radical, and then b, and then we have the same but with a minus. So let's go ahead and multiply both sides by this denominator on the left, and you get 1 equals a x minus radical negative k b x plus radical negative k. And then let's go ahead and pull out x there. And then we're left over with our constant. That's a minus there. So on the left, we see that there's no x term on the left. So over here, a must a plus b must be 0. The constant term on the left is 1, so that means the constant term over here with no x, that must be 1. So let me go ahead and write this on the next page. We have b root negative k minus a root negative k equals 1. I also had a plus b equals 0. So solve the second equation, and then go ahead and plug in b equals negative a over here, and then solve for a. And now we have a, and then using this, we find b. And now we go ahead and plug in those a and b into our partial fraction composition, and now we're ready to integrate. So there's our a dx, and now we have our b. Now if this plus and minus, the radical, bothering you, feel free to do a sub of this form for the first, for the second, very similar. In any case, when we go ahead and integrate that, we should have to pull out that constant, so negative 1 over 2 root negative k, and then natural log absolute value x plus radical negative k. And then for the second one, 1 over 2 root negative k, natural log x minus radical negative k. And of course, the terms can be combined using the log properties. And then we have our constant c of integration. So this is our answer in case 3 when k was negative.